To introduce Dr. Bruno Fernandes, postdoctoral fellow in the Center for Subsurface Energy and the Environment at the University of Texas at Austin. He received his Bachelor's of Science in Chemical Engineering from the Federal University of Ceará, Brazil in 2011. He received his Master's in Chemical Engineering from the same university in 2014. Received his PhD in Petroleum Engineering from the top University of Texas at Austin in 2019. He's authored or co-authored over 27 publications. Wow. His interests are on numerical methods applied to reservoir engineering problems, especially those involving time discretization, gridding, and spatial discretization techniques. All right, Dr. Fernandes, you now have the room. Go ahead.
All right. Well, thank you so much, Dr. Perch, for the introduction, and also to Dr. Balhoff for the invitation, right? So today, as Dr. Perch was presenting me, I just would like to mention that I'm working with Dr. Cami Sapernori group, mainly in reservoir simulation. And today I would like to go over overview of the discretization schemes that in compositional reservoir simulation that I have been involved in my research group, right? So for this presentation, we're going to first introduce the problem of the compositional reservoir simulation. I'm going to talk a little about the gridding approaches that I have worked on, also the high resolution schemes, and finally, I'm going to go over a brief description of the time discretization algorithms that we have worked on. So just to give you a description of my research group, the Reservoir Simulation Joint Industry Project is mainly focused on a reservoir simulation, but we also work on other areas, such as flow assurance, low salinity, and so on. And currently, we actually we are supporting two simulators, UTCOMPRS and UTCOMPRS. Our UTCOMPRS being the compositional reservoir simulator, and is going to be the focus on of this presentation. With these two simulators, we are able to model many different types of processes, such as chemical EOR, thermal, compositional, black hole geochemistry, and geomechanics. So as we know, oil and gas are found into reservoir rock. I guess I should admit, are found in reservoir rocks, in the pores of reservoir rocks. So we need Darcy's law in order to describe the fluid flow in porous media, right? And in order to describe this fluid flow in the porous media, we combine Darcy's law and material balance equations, such as we see here. And the important thing about the compositional model is that we describe the hydrocarbon phases by a multi-component mixture of different hydrocarbons, right? This could be 5 components, 10 components, 20 components, and so on, right? And then we also have our water component, right? For the sake of this presentation here, we assume that there is no mass transfer between hydrocarbon components and aqueous phase, the hydrocarbon phases and the aqueous phase. And here we have, just to describe the equation for you, we have our accumulation term, our advection term here, which is described in Darcy's law, and our dispersion term, along with the well term. So for this type of problem, we need mainly our material balance for each hydrocarbon component, the water component, and the volume constraint equation. Okay, so the phase behavior of the hydrocarbon phases is described in a modified Peng-Robinson equation of state. We assume a local equilibrium, a local thermodynamic equilibrium, and the number of phases for this type of problem are calculated using a phase stability analysis, a phase stability method, which is followed by a flash calculation for compute phase compositions of each phase and also the amount, basically the mole fraction of each hydrocarbon phase. this approach is not done for the aqueous phase. Now, we have seen that our material balance equations are partial differential equations. So we do have a set of partial differential equations. And what we need to do is we need to solve these equations if we want to estimate the amount of oil that we can produce, right? And do all of the engineering things that we need, such as optimization, history matching, and so on. In order to do that, we need to perform a time and spatial discretization of our partial differential equations. This is gonna convert our PDEs into a system of nonlinear equations, and we can use a linearization technique such as the Newton's method to convert this into a system of linear equations. And the system of linear equations we are very familiar to how to solve. In this work here, our discretization technique is basically the finite volume method. So it's basically, we take our PDEs and we integrate them in time and space. So here for a quick note on the time discretization that we're gonna be looking later, right? If we have an ordinary differential equation, ODE with the following form and we integrate it in time, then we're gonna need to approximate our function f here, the right-hand side of function in time, right, in order to calculate this approximate integral. So if we estimate this at the previous time step, which we know the previous time step, so everything at time n we know, okay, this is gonna give us a method that we call explicit. If we approximate these at the next time step level, then we're gonna get a full implicit. So at the next time step level, we don't know these unknowns or functions, and therefore this is gonna become strongly nonlinear, right? Now, we may select part of these variables to be treated implicitly and part of these variables or functions to be treated explicitly. So we're gonna be using actually n plus theta along this presentation in order to describe variables that can assume both possible values, right? So if it's 0, it's gonna be explicit. If it's 1, it's gonna be implicit. Now, again, we take our material balance equations and we integrate them in time and space into a arbitrary control volume. So it's not in the whole space, actually in the arbitrary control volume. So we're gonna end up with several equations to solve. And then we apply the Green-Gauss theorem. So the Green-Gauss theorem is gonna change our volume integral into an area integral. And it's also gonna remove the divergent that we would have here. Please note that here, we have already this side of the equation actually integrated in time. And what we see here are the thetas that I described, and the pressure already is n plus 1. And this is because in petroleum engineering, we normally would assume that the pressure is always implicit. All right, so what we do next is we approximate the integral into a discrete summation of the different areas. So if we have an arbitrary control volume here, right, with 6 faces here, we'll have actually our NF, which is the number of faces, equals to 6. And we have this whole term here. And each of these terms are evaluated at the interfaces right here. Now, this is important to mention because our unknowns are actually calculated usually at the center of our grid blocks or our control volumes. So we don't really know the values at the interface. We are actually estimating them, right? So this whole property here, we're gonna see later how to estimate that. And so we're gonna be actually discussing on this term here, right, at the interface. And we need to approximate this basically gradient and areas and so on, right? So if we take the flux, and of course, I'm sorry, let me just go back here. This whole term here is gonna be mole flux, okay? So if we take the flux for a given interface, let's say, for example, interface 3 here, this control volume, and we expand this whole operation here, you're gonna get this big equation here. And the important thing to mention, to notice is that we have here these derivatives with respect to x, y, and so on, right? Now, how would you calculate this if your grid is tilted or if you have very complex grid, right? This is where the different grid techniques, they come into place. So grids, they can be of two types. They can be structured grids or unstructured grids. And for the structured grids here, we're gonna be, I'm sorry, discussing Cartesian grids and curvilinear grids. So Cartesian grids, we're gonna have actually our terms being reduced to a very simplified version of it. We assume that our off-diagonal terms of the permeability tensor are 0. And also all of the phases, all of our integrals of our normal area vectors, they are aligned to a single axis. So for example, here we have our area described here as E aligned with the x-axis, right? And therefore we have this simplification. We only have here delta AX. And if we further use here finite difference to approximate this derivative, we're gonna get this final form here. In this whole term here, we normally group and call it transmissibility. Now, it is important here to see that for each of these fluxes, we're gonna have 2 points involved, the grid block in which we are computing the material balance and the neighbor grid block, right, which shares that interface, right? So this is what we would call a 2-point approximation, right? Now for curvilinear grids, we have many different techniques for handling this kind of problem, right? So the curvilinear grids or corner point grids, as they are more known in the oil industry, are grids in which they are still structured, but the grid lines, they don't need to be aligned with the x-axis. They can actually deform, right? But they are still structured. So with that, what that means is that we still have the same connectivity pattern in this type of problem as we would have in Cartesian. And the boundary filter approach is a method that basically takes our grid in the physical domain, in the x and y domain, and we make a coordinate transformation to a c eta domain. And in this transformed domain, we basically have our grid being completely regular. And actually, even these sizes here are equals to 1 in this transformed domain, right? Now, the difficulty here is that we actually convert our material balance equations from the physical domain into a material balance equation on our transformed domain or computational plane, as we would like to call, right? And we see that now we have here derivatives with respect to C and derivatives with respect to eta, and we have these actually crossed terms here, which are terms that are going to account for the non-orthogonality of the grid. So this distortion, deviation of the grid lines in respect to x and y directions, right? And as such, these values here that we see, D11, D12, right? They are not going to be 0, even if your permeability tensor only has diagonal terms, right? And this is to account for this non-orthogonality. Now, you could force these terms to be 0, these off-diagonal terms here, and have only D11 and D22 and D33, and you'd have what we would call an orthogonal boundary fitted approach, right? But we will see the consequences of doing that later, all right? Now, another approach is the vector approach, which is very similar to the Cartesian in the sense of the discretization, but here we actually have a different way for calculating the transmissibility, right? Which takes a little bit into account the curvature of the grid lines, right? And the greatest advantage of this method is actually that we can handle what we call hanging nodes. So as you see here, we can have 2 grid blocks that they are not fully connected here in this area, right? So hanging nodes are usually commonly used for mapping faults in our problems. So if we look at this here, in this case, we would have actually our grid having to be divided into two blocks. If we were to use a boundary fitted approach, we'd have to take this part here of the grid and do a domain transformation here, and this other part of the grid and do a domain transformation separate, and then use a periodic boundary condition to have the flux between these two different grids, right? Each of these grids are called blocks. And as you may realize, it becomes very complicated to do this kind of processing if you have several faults in your problem. That's why we didn't really implement the multi-block boundary fitted approach in UTCOMPRS, only the boundary fitted regular boundary fitted approach. Now, I was mentioning about the orthogonality of the grid and all of that. So what are the effects of neglecting these terms? So here we have an example where we actually consider the non-orthogonality or the non-orthogonal terms for the boundary fitted approach. And you can see that here, even though the grid lines are very distorted, we still have somewhat symmetric front of gas. But if we neglect these non-orthogonal terms, we are going to have a very distorted front, right? What about the vector approach? Well, the vector approach doesn't account for the non-orthogonality very well. So we still have huge grid orientation effect. Okay, by the way, this is called grid orientation effect. Even if we have a mobility ratio that is very low. Now, if we increase the mobility ratio, then this actually gets much worse, right? But this is not something that like you would think, oh, okay, so nobody uses vector approach. No, actually the vector approach is the default method used in commercial simulators. Although many commercial simulators also have approaches that can handle this non-orthogonality better, right? But they are computationally more expensive, okay? The only thing we need to know is that we need to be very careful when we are distorting the grid lines, not to have to make it too bad for the solution, right? Now, as for unstructured grids, we can have two types of unstructured grids. We can have cell-centered unstructured grids, where our unknowns are stored into the cells or the elements, right? And so in this regard, you could say that every structured grid is a cell-centered approach, right? Because your unknowns are on the blocks. Or you could have your unknowns, such as pressure, saturation, right? Number of moles and so on, being stored around the nodes of the grids or the vertices, right? For this type of approach, you need to actually create another grid around your nodes. And this is what we would call dual grid or dual mesh approach, right? We have two techniques implemented, the diamond cells for cell center and the element-based finite volume method for vertex center, right? So for the diamond cell approach, we have our element grid, and you could have for these elements anything like a triangle or quadrilateral or a pentagon. And what we do is we take each of these faces here of these interfaces between blocks, say for instance here between block 1 and 2, and we take the centers of these two blocks and we connect to the vertices that are sharing this edge, right, or this area here between the two grid blocks. This is going to create a quadrilateral, and what we do is we take this quadrilateral and do a local plane transformation, right, to a xc eta plane here, and in this plane here, we use actually shape functions from the Galeckin method to calculate the derivatives with respect to x and y, right? Another thing that's interesting to notice about this method is that the stencil for this flux is going to be very big. We're going to have nodes 1 and 2, and all of these gray grid blocks here are going to be contributing for the flux in this interface between blocks 1 and 2, right? So this gives a way less grid orientation effect, for instance. And here's the way that this local transformation works. So basically, you can calculate the derivative of phi using this equation where ni are what we call shape functions, right? So shape functions, they are predefined by the element that you are using. You can look in the literature if you want to use a triangle or a quadrilateral and so on, right? And here we have how to calculate these derivatives. The other approach that we use for Vertex centered is the element-based finite volume, or more commonly known as control volume finite element method, right? And here we actually take our elements and we're gonna divide the elements into pieces that we call sub-control volumes, right? So here we are dividing this quadrilateral, for instance, into 4 pieces. Each piece is gonna belong to one of the nodes composing the element that we have. So if we have a triangle, as for example here, we're gonna have actually the triangle being divided into 3 pieces, right? And when we combine these pieces here, we get our grid block for node 5. So if we were to combine here these 2 pieces, we'd have our grid block for node 6, right? And what we need here is the flux across this interface, which are internal to the elements. So each element, for example, here quadrilateral, they have 4 interfaces within this, and the triangle 3 interfaces, and so on, right? So the procedure for calculating derivatives within the element are actually very similar to what we did with the diamond cell approach that we have, which I call an element-based diamond cell. It's important to mention that that diamond cell is not really the original diamond cell approach that some people use, in which we actually use, here we use a shape function to do this local transformation, right? So we transform from our physical plane. Each element individual is transformed to a computational plane in which all of the elements, they look the same in this computational plane, right? And then we can calculate properties using our shape functions and also derivatives. So how does the cell center approach and the vertex center approach compare for this problem, right? So here we have a gas flood in a reservoir. The grid is exactly the same. The only difference is that we have here we're solving with vertex-centered method, and here with the diamond cell method, right? And as you can see, results are very close. Now, we did do some comparisons to test the performance of these methods, right? For example, here we have a CO2 injection in a homogeneous quarter-5 spot. And the advantage of this is that we can compare these results with the Cartesian grid without any issue. And we can see that the Cartesian grid, as we change the number of control volumes, is much cheaper than the our element-based or our unstructured grid approach. And this is because of the stencil of the unstructured grid, which is big in these cases, right? And we also see that as we increase the number of blocks or control volumes, we actually have that the vertex center approach becomes more expensive than our cell center approach, right? We do another test, but now we consider a flow permeability tensor. So for the flow permeability tensor, we cannot use Cartesian grid anymore. And we actually see that the behavior is the same. We still have the cell center method being more cheaper than the cell vertex method, right? Now, the vertex center method was supposed to be more accurate, or we didn't see this accuracy improvement as being so significant, okay? And here we have just, to exemplify the solution that we have for 3D ABFEM method, or the vertex-centered approach, right? We didn't implement our cell center for 3D yet. It's a little bit more complicated for 3D, I'm sorry. But as you can see in these grids here, we can basically use different refinement easily within the well. So you can use different elements. Actually, you have mostly hexahedrons in these 2 grids. but next to the wells, we use actual tetrahedrons and pyramids and prisms and so on. Now, to discuss about the other term that we mentioned before, right? We have here the property that is going to be multiplying this huge piece here, which we handle with our grid techniques, right? So traditionally, let us call this as delta F to simplify. And traditionally, we use a method called upwind or upstream, in which we take the direction of the flow. So if the flow is going here from block A to B, then the property at block F would be equal to the property at block A. And if the flow is going from block B to A, you would take the property at the interface as being equal to the property at block B, right? Now, this is a first order approximation, and the reason we don't use an average, for example, you may think like, okay, why don't you just say that property at interface is simply an average between block A and B? Well, if we do that, we'll get an unstable solution, and then we'll get oscillation. Although it would look perhaps more accurate, it would be full of oscillation, right? In order to avoid oscillation, these are all different methods in the literature that are used to handle this oscillation, right? And to make us able to have higher resolution. We tested in UTCOMP all TVD, NVD, and MLP methods, but they were all very similar to each other in terms of results. So that's why here I'm going to be presenting only the TVD approach. So for the TVD approach, we are trying to preserve the monotonicity of the solution, right? And the way we do this is by using a flux limiter. So through many research, we have found out that if we have our interface property being calculated as the upstream plus this here flux limiter, and this difference here. So if our flux limiter is 1, we would have a average, and that would give us unstable, right? Depending on actually our flux limiter here, our successive slope ratio, right? So if our flux limiter is within this gray region here, we have stable solution. So we want it to stay within this gray region, right? And what we need is we need an extra point. We need what we call a far upstream point, right? And also the downstream point. But there is no far upstream point if we go for an arbitrary grid. Say you go to a corner point grid with lots of distortion, or you go to a unstructured grid like here, right? Your far upstream, you cannot really figure what is the far upstream between this interface here, right? So what we do is we make use of a gradient reconstruction, which would be the gradient of our upstream property, and we project it on the back so that we can estimate a value for the far upstream node, right? So this looks very complicated, but it's not that complicated. And with this, we can actually use the flux limiters in the literature. We have here the lower flux limiter, the lower limit flux limiter, which is the min mod, and the upper limit, which is the super B. And we have Liu et al., which is the flux limiter we are using in this work here. And it was developed at UT in 1994. And here we have a comparison, actually, of how these different techniques, they are going to approach the accuracy, right? So we have here our exact solution. If we look here at Liu et al., for a grid with only 100 elements, we have a much better resolution than, for example, with upstream, right? And if we refine the grid, basically our two TVD approaches using min mode and Liu et al. Flux limiters, they already reached the solution, but the upwind approach is still not there, even with 2000 elements. And here we can actually plot the L1 norm of the errors using for that problem using different grid sizes, right? And we would see that the errors, they grow quite differently, and we can approximate it. And we can use these exponents here, right, to determine the order of the approximation, right? So as we see here, if we can obtain third order if our L1 norm is as this exponent larger than 3.4, 3/4, or 3/4. So Liu et al., even for unstructured grid, it still reaches third order approximation. We can also see the effects of the grid orientation for the TVD, right? We can here run a case here with diagonal grid. These are all both triangles, but as you see here, the grid lines are connecting the two walls, and here the grid lines are actually in a different pattern here, not connecting the walls, right? And we can see that if we look here at diagonal, we have a much sharper front when using Liu et al. Versus when using upwind, right? Also for the parallel grid, we have a much smoother front when using upstream and much sharper front when using Liu et al., showing that Liu et al. Can really reduce quite significantly the numerical dispersion. And here we show, just showcase a result for a 2D grid, right? Complex 2D grid here. And if we look carefully, we can also see very smooth here for upstream, but for Liu et al., our TVD, we have a much sharper front. We actually have already the red region here breaking through into the producer, right? Now, the final topic that I would like to cover here would be about the time discretization, right, of the data that we have been discussing. So it is well known in the industry, you have two types of time discretization, or classes of time discretization techniques. It would be the impact and the full implicit. We also have the IMSAT approach, but I'm not going to be discussing about it here. So in the impact, only the pressure is implicit, right? Now, impact has the advantage of having been very cheap for time steps. So if we look at the calculation we need to do for a single time step, the linear solve is much smaller. You don't need a very big Jacobian and so on and so on, right? So very cheap versus the full implicit, which needs a very large Jacobian. You need to do you always need to do Newton-Raphson method, right? So several iterations. Not all impact approaches require you to do Newton's method, but there is a problem with the impact approach. And the problem is that due to stability, we have a limit at the time step size that we can use. And if we use time steps that are too large, we're gonna get here some oscillation in the solution. And this oscillation can be really bad. Here, this is a mild oscillation. So you want to really have a solution, right? While for the full implicit, we actually have, we are able to use, in theory, any time step size, right? In fact, in reality, you are limited by accuracy and also by the convergence of the Newton's method, right? But this gives way more flexibility for the full implicit method. Now, we can combine these two approaches. We can combine the low cost of impact with the large time step from full implicit by selecting dynamically in the reservoir grid blocks to be full implicit and some other grid blocks to be impact, right? This is what we call adaptive implicit, right? Now, adaptive implicit methods, they're going to be successful if they can have most of their grid blocks as impact, right? Because there will be also some issues associated with this dynamic change in the basically Jacobian that we have as we change our values. Now, how do we select the implicitness? The implicitness comes from the stability of the explicit variables, right? For instance, explicit saturation and explicit composition. So, for example, if it is stable to use both explicit saturation and explicit composition in a grid block, then you can use it as impact. If either of these explicit saturation or explicit composition are not possible, then you have to use full implicit, right? And the way we do that is we do certain assumptions, right? We do use a Buckley-Leverett model to obtain an error equation. And here we have a T, which we call an amplification matrix. And if we get our eigenvalues for it, if they are all smaller than 1, then we can use full implicit, right? So this is a list of the different formulations that we have implemented into UTCOMPRS. We have here the impact, which is the original formulation from UTCOMP, even before UTCOMPRS, right? We also implemented IMSAT, different IMSAT approaches, also implicit pressure and saturations, but I'm not going to be discussing about that here in this talk. And then we have a list of different full implicit algorithms that we have implemented. We even designed our own full implicit, which we call PZS, because of the primary variables that we are solving for. And we further improved it to become an adaptive implicit approach, right? So here, the PZS is really an extension of the Collins et al. Formulation. So we start from the Collins et al. Formulation and we do a variable change into P, Z, and S. And you may ask, what is the difference? Well, the difference here is that here we have pen and number of moles. This is an extensive variable set. And here we have P, Z, and S. This is an intensive variable set. So you need one less equation to define the system, right? So just to exemplify here how the adaptive implicit works, if we have 2 blocks being full implicit and 2 blocks impact, we will get the following structure for our Jacobian, right? So as you see, we have here this diagonal format for the impact grid main blocks, right? And the off diagonal terms involving impact grid blocks, they only have here terms of pressure, right? So we can take advantage of this format, of this type of Jacobian structure, and actually reduce the linear system size to something that is much smaller, right? And that's why it becomes much cheaper to use AIM in many situations, right? Is the AIM always cheaper than full implicit? No, it depends on the case, right? For example, in this case here, you have a gas floating in a heterogeneous reservoir, 3 phases. We have about 256,000 grid blocks, right? Heterogeneous. And here we have a comparison of the solution, right? Oil, gas, and also time step. We see that all the full implicit and adaptive implicit are using about 1 day of time step size. Here we had to cap the time step. This was the best time step profile that we could get with the impact. We could actually go even further with the implicit and adaptive implicit methods, but we would lose quite a bit of accuracy, right? And when we look at gas saturations, right, the different approach that we are using for time discretization, remember these are all full implicit or adaptive implicit, right? They are all first order approximation in time. So you want to get very similar results, right? If you were using Crank-Nicholson and you could avoid oscillations, then you'd get more accurate results, actually. Now, if we look in terms of performance, we're going to see that our PZS full implicit was the fastest approach, running in about 1 hour for this case, and the impact was the slowest approach, running in about 53 times more than the PZS approach, right? Adaptive implicit was only a little bit slower than the PZS, And this is explained because there is a huge amount of grid blocks that are fully implicit in this problem. And the issue with having a large implicitness is that we need, every time we change our structure of the matrix, we need to redo the ILU preconditioning of our matrix. We need to change the structure of that ILU preconditioning, and that is also very expensive. And this is also the overhead. Following, we have here a four-phase CO2 flooding. This is a case with four phases. So as far as we know, only UTCOMPRS can handle this kind of problem. And we have 400,000 grid blocks for only about 100,000 active cells. And here we have a comparison of the different profiles. We do not have here profiles for impact and codes because they fail for this approach, for this problem. And we compare the fields, gas saturation fields at 1,000 days, which look basically the same. Now, in terms of performance, they look all very similar aside from codes and impact, which could not really perform the run. And having here the adaptive implicit PZS being the most the fastest approach, right? Followed by its counterpart, its full implicit counterpart, PZS, with 24% more cost, and then the colonies approach, right? So finally here, for the final case, we just would like to showcase here our water and gas injection in a reservoir. This is the non-geological data, right? So this is a corner point grid for a real field case. And we basically use an adaptive implicit approach for this problem, right? We don't have any other approach that can be used here. We use the adaptive implicit PZS on this. And here we have initial water saturation, initial pressure, and here we have the solution, right? The greatest advantage of using an adaptive implicit or full implicit is that we don't need to worry about oscillation, right? So we simply run once and we know that we're not gonna get any oscillation in our plots, right? So finally, we have implemented different grid techniques in UTCOMP. They all have their shortcomings and also their advantages, right? We have seen that the vector approach, for instance, is very flexible in handling faults, but it lacks the ability to handle the non-orthogonality of the grid more properly, right? We have also seen the TVD approach, right, for improving the resolution of our basically advection dominated problems, right? And we use Liu et al., which was designed for Cartesian grids, for unstructured grids. And it is important to mention that that approach that we designed can also be used for corner point grids. And finally, we were able to represent very complex reservoirs that are used in real application with our CPG vector method, right? And from the implicit approaches that were implemented and tested, we developed a new approach called PZS. We also implemented that approach into an adaptive implicit framework with actually the implicit selection is also developed by us. And we have seen that in many cases, the PZS is the best, is the fastest approach when compared to both codes and columns, which are the other two full implicits that we have. Right. All right, so with this, I conclude my talk. So I'll be glad to answer any questions that you may have.
All right, Dr. Fernandes, thank you very much for this very informative presentation. We really do appreciate it. I want to give the first opportunity to students. Any students with any questions?
Hello, can I ask a question?
Go ahead.
Hello, Dr. Fernandes. Thank you so much for that presentation. The math is, I think, beyond anything I learned in engineering analysis. So on slide 40, you had a grid where you had some blocks chosen as impact and some as FI. Just to be clear, did you manually choose those blocks, or did you use some sort of algorithm to decide?
Okay, so this here is an illustration, right? This here is an illustration. I guess I went too fast on it, which is the problem of covering so much in a talk. But usually what we do is we select the blocks that have wells as being always full implicit, because you have a high rate in there, right? A high velocity in these blocks. And you're also gonna get usually, right, blocks around the front, the moving front, like your gas, or maybe you have a CO2 front or water. So the grid blocks at the front are gonna be also handled as full implicit. Now, this comes from stability analysis, right? We select the wells to be full implicit because we know it needs to be full implicit. Now, the front, we calculate with the stability analysis. So for doing that, you actually need to write down the error equations for it. For explicit composition, as you see, it's a little bit easier to do it, right? But for saturations, it may become very complicated.
Okay, thank you.
Okay.
Thank you very much, Barun. Any other questions from students? All right, we'll open up the floor to any questions from faculty or students. Anyone?
Yes,
Dr.
can I ask a question?
Dr. Delshad, of course, please, thank you.
Bruno, would you please go to the case that you called it water, gas, and actual field case?
Yeah.
So what is the gas here?
Oh, the gas here, if I recall, this is CO2.
It was a CO2. So when you
Yeah.
say is a three-component compositional, what are the three components?
Yeah, I'm trying. Oh, I'm sorry. This is, I guess, this C1, C3, and C10.
Okay, so it's a hydrocarbon gas.
Yeah, it's a hydrocarbon gas.
But I think this isn't that one of the cases that they did a comparative study for CO2 injection? Or I'm making a mistake, because the reservoir shape is very familiar with one of the.
Yeah, no. So this is actually the fluid, and the well pattern, all of that is I synthetically added. What I took here was the geological model, so permeability, porosity, the grid, all of that, right?
Right.
From the non-field. So this
Okay.
is a geological model from Equinor.
Equinor, yeah. Okay.
That's probably why.
The question I have, I know you're not comfortable to say that, but in terms of the speed, how does your code compare with, let's say, Intersect or CMG?
We never compared it with Intersect per se. We did compare with CMG and Eclipse. And for example, if we think about unconventional, of course, this is also implemented with EDFM. I didn't present any EDFM result here, but for unconventional, we are pretty much comparable to CMG and Eclipse, unless Eclipse is using CPR, the CPR solver, right? Okay. Then Eclipse becomes much faster, to be honest. But if we are talking about conventional, then we are also very close to CMG, especially CMG. We are slightly faster than CMG. Eclipse usually is slightly faster than us.
Okay, that's good to know. Thank you so much. Mm-hmm. Yeah, that's very helpful. Thank you.
Thank you very much, Dr. Delshad. Other questions from anyone? Dr. Fernandes, while people are thinking, I'll ask a quick question. I come from the reservoir modeling world, and you're presenting all kinds of very complicated grids. Can you just comment on how do we get the reservoir models to those grids? How do we get the permeability models, the heterogeneity models?
Oh, this has actually been a topic of huge discussion while we were actually using unstructured grids, right? Especially in a Petrobras project, right? Even constructing the grid, we use it to work a software because there is no software to make unstructured grid for reservoir engineering, right? They say there is one, but really we tested it. It wasn't really. It was more like a corner point grid, and we tried using a software from ANSYS called ISAM, but we would always end up with all kinds of problems in the grid that was generated. We need to do a lot of treating, like nodes overlapping and elements overlapping and all of that. Yep. So the idea that we have been having recently was to actually use corner point grids because people are already familiar with it. And, this type of grid, for instance, right, there is no problem in solving it with an unstructured grid, right? All we need to do is look at the faults. We'll do some refining close to the faults, right? Some more refining, adding some extra points in the connections, and then use the unstructured grid. They are actually working on it because especially it is hard to get data for unstructured grids, right? And we are not geologists. I'm not that familiar with generating this data for.
I would suggest you're probably at a point where you're leading ahead of the reservoir modeling community and you need them to catch up. Many of the geostats approaches actually assume regular Cartesian grids. So they're going to have to catch up with you. No, thank you very much. Any other questions from the group? All right. All right, I think we've exhausted. Dr. Fernandes, thank you very much for joining in the graduate seminar series. We appreciate you sharing your knowledge and experience with us.